Alright, what is going on, guys? Today we're going to continue with Chern-Simons three forms in the context of topological QCD. We're kind of doing a little bit of a detour here, as I've mentioned before. Also, two things I want to get clear before we continue here. I've been pronouncing Chern-Simons wrong. That is my bad. I don't think when I speak sometimes it's Simons, like not Simmons, right? So for the past video or so, I've been saying Simmons, like Gene Simmons from Kiss. It's not that. It's Simons. Just to get that clear, that's how it's pronounced. Also, I had made a typo. The typo was here. This this guy right here. This was the exterior derivative, right? Exterior derivative, and that just wasn't in my last video. It was carried on through the derivation. I double checked. It was carried on through the derivation. Someone kindly pointed out that I somehow just dropped it at the end, and so my apologies for that. Let's go ahead and get started with Chern-Simons three-form transformations. Again, if it just slips out and I mispronounce it, my apologies for that. Jim Simons is a very, very well-renowned economist and physicist. He was a very interesting figure within the area of physics because of his contributions to these topological field theories. And Chern, personally, I don't really know a lot about Chern. I know his name is Shin-Chen Chern, or something like that. Again, if my pronunciation is bad, feel free to correct me on that. But I don't know as much as about him than I do Simons. So, okay, that's my correction. Let's go ahead and get started. So we're going to dive deep into the concept of Chern-Simons theory for the next few videos before we move on to lattice QCD. A lot of these videos are going to be even more complete on my website when it comes out. They're going to be organized a little bit better, and you'll be able to download these notes as well on my website per video. So let's just recall what we've done so far. This was the electromagnetic, or this was the Yang-Mills theory, right? This was Yang-Mills. So I'll write that right here, Yang-Mills theory. And we were able to get a field strength tensor F. Sometimes it'll be written G. This is our field strength tensor. And our field strength tensor had a geometric form, right? And that's the form we all know and love, right? That's the d mu a nu minus d nu a mu plus I g, the commutator between a mu b with a nu c. And then hidden within all this are these matrices that are proportional to the Gelman matrices. Gelman being SU3 matrices, right? So this is SU3. We're looking at, this is QCD. These words are essentially synonymous with each other. On the other hand, we were able to see that we were also able to write a topological version of our field strength tensor. And that topological version was the exterior derivative of our electromagnetic field potential, or not electromagnetic, but our potential. Okay, so we had this was the exterior derivative again, and make sure my mic is okay, and the wedge product between the field with itself. So this is the wedge product. This comes from geometric algebra. This is a concept in geometric algebra, right? Geometric algebra is super, super interesting. I'm going to dedicate an entire playlist to geometric algebra on my website when that comes out. So be on the lookout for that. And we were able to write the topological field strength tensor or use the topological field strength tensor to define something called a theta term. That's this bit right here. That's the trace of the strength tensor, the field strength tensor, wedged with itself. And we were able to see that that's equal to the exterior derivative of some 3 form that we're calling the Chern-Simons 3 form. Okay. Now this is going to be interesting because we're going to invoke Stokes' theorem here to notice something about the nature of this theta term, what it actually means, what it actually entails. So let's continue with the derivation here. So let's define a quantity called the instanton number, instanton, however you pronounce it. Again, I also want to be super clear. Some of these courses I have taken formal classes in, like quantum field theory, I've Chern-Simons theory, and so I've taken some formal courses in those. I have also taken not formal courses in some of this concepts as well. The non-formal is mostly for me just reading a bunch of PDFs and books. So this is coming from a mix of formal courses and reading and sort of informally learning about this myself as well. But a large portion of this QCD, it comes from formal understandings and courses that I've taken. So let's define a quantity called the instanton number, and this is a topological invariant, and it doesn't change under smooth deformations of the gauge field, and for fields at infinity. And a lot of this can become clear later. And it's always an integer. This is a thing that's quantized, okay? Which is going to be interesting to see. We're not going to exactly see that in this video, but we want to keep that in mind, that this Q is quantized. It can be 1, it can be 2, it can be -1. And when it's 1 or 2 and it's positive, we're going to call it instantons. So instantons. And when it's a negative number, it's going to be an anti-instanton, okay? We're jumping ahead a little much, but I'm sort of prepping you for what's to come before we start diving into lattice QCD. But it counts. This number is going to count the number of instantons, right? So we have 1, 2, 3, and it's going to have to do with. I won't get too far ahead of myself here, but we're defining this thing. It counts the number of instantons. If it's negative, it's going to be an anti-instanton. And this is the theta term, right? This here is the theta term, right? And so the theta term, we said, was the exterior derivative of the Chern-Simons 3 form, okay? And that's right here, right? So we're calling this omega 3, that's all of this, okay? So now we have an integral of an exact form. Okay, we'll see exactly what an exact form is. Well, we're going to review a little bit of cohomology here before we dive into this. But the point here is that we're going to be able to do a Stokes theorem on this. And this is a powerful insight because, again, like I just said, we'll be able to invoke Stokes theorem to infer meaning from this. So first, let's brush up on our homology and cohomology. If you don't really know this stuff, if you want to dive deep into these concepts, I do have full intention to make playlists that automatically come out on my website as well for these concepts. But we're going to do a quick rundown, hopefully in a way that is mathematically somewhat intuitive to understand, but we're not going to dive deep into the math here. We just kind of want to review. The way I like to view cohomology is sort of a more quantitative approach to homology, and it's a little bit more tangible, mathematically tangible, and easier to understand, I think, in my view. Some people might disagree with me on that. They might think homology is a little bit more tangible because it deals with simplices more than it does, or more so than it does with wedge products. But the idea here is that simplexes or simplices are the way we define boundaries on them is going to be very similar to how we do exterior derivatives on forms. So the exterior derivatives on forms, that's going to be encapsulated in the cohomology, and the simplices, something that we call a boundary operator on simplices has to do with homology. So, and this all falls under the category of topology, right? If we want to count the number of holes in some object, that's topology, right? The number of holes in some object is a quantized number, right? So we could start talking about topological quantum field theories and stuff like this. So, okay, so let's suppose we start with some function here. We could take the exterior derivative of this function, and we're going to call the exterior derivative of this function omega. Okay, so here's omega. And then we could take the exterior derivative again of omega, and we get this thing. This is going to be an exact form, right? So we can take the exterior derivative of this, and we get the exterior derivative of omega. I'm not going to write the whole thing out, but we're going to get exterior derivatives when we take it twice of something. That's going to be 0, right? So that's going to be what's called an exact form. When you take the exterior derivative twice you get 0. This is also the nilpotent condition that you might have heard of before. But there's also going to be areas within, points within this omega that also don't have a derivative, right? So if we set the exterior derivative of this equal to 0, we can get d omega, but there's also a point where x equals y equals 0. It's the origin, and if x equals y, which equals 0, then we see the denominator of these guys is undefined, right? So that's an undefined region on this form. This undefined region on the form is undefined, and what we want to do when we start looking at cohomology is we want to take a look at this space here, and we want to be able to just count these things here, the regions that are undefined. Okay, so when we take the regions that are undefined, and we could count those. That's going to be the cohomology of what we're studying. Okay, and so one way of thinking about this, one way that I like to think about this, is that we're siphoning off these guys here. Okay, so we're going to write the cohomology group as cohomology group N, where we have N is the dimension of the space on the manifold, is equal to Zn on the manifold, and this is on the manifold as well. Modded, when we mod out, this is sort of the nomenclature here, we mod out B n on the manifold, right? That's this guy right here. So we're modding out this space from this space, and when we do that, we're effectively ignoring this, and we're just counting these undefined regions, okay? And the undefined regions are the holes in our space. This is a very topological way of looking, an algebraic and a very topological way of looking at our manifolds. All right. So homology takes a more visual approach, but I like this. We could take the exterior derivative of this thing, right? We can take the boundary operator. Actually, this thing is called the boundary operator. It's different. Right, boundary operator, whereas in the cohomology case we were looking at an exterior derivative. The point here is that the boundary operator and the exterior derivative behave very similarly to one another when they act on simplices and forms respectively, right? So when we take the boundary operator of this and then we take the boundary operator of this, we get this looking thing, right? Because the boundary of this thing is going to be these points here, but we can also look at this and we can see, well, it's not quite obvious that these red points are the boundaries of the lines. It could be that the lines are the boundaries of the points, right? So one way of thinking about this is to say, well, when we take the boundary operator again on this object, we get this, and the result here is 0, okay? because these are just points. And the reason they're 0, again, you can go into my Chern-Simons playlist where we can actually do an example. I actually did an example as to just to show why this situation actually equaled 0. But the other thing we can do is we can say, well, we can take Zn, right? So Zn is going to be, we're taking the kernel of, you know what? We're taking the kernel of the situation, but instead we're taking the non-trivial part of this, right? So there's going to be, this is like a trivial, this is going to be like the trivial boundary. And this is sort of the untrivial boundary. The untrivial boundary is the thing that has the hole in it, right? There's a big hole right here. Right? We can color this hole in, but the point here is that the non-trivial boundary is the thing that has a hole in it. We're counting holes, right? So this is, we want to be able to siphon this thing out of this space, and the way we do that is we take Zn and we mod out Bn, okay? But here's the thing that I want to get across here. Again, that was sort of a review of homology and cohomology, but the thing that I want to get across is that these things are called exact forms. Right? These things are called exact forms when the boundary of this thing, or whatever we're dealing with here, is 0. Okay? One way of thinking about this is we're saying we're taking the space of all the things that could be boundaries, okay, and then we're modding out the thing that actually is a boundary. What we're left with is the thing that's sort of this untrivial boundary, if you will, right? So, and that's this thing right here. So here we are. So this is our summary, right? We have these things called closed forms. Those are the things that could be boundaries, but then we have exact forms. These are things that are exactly boundaries. We mod the things out that are exactly boundaries, and the result is something that is a boundary. It's closed, but it's not trivial, right? So, and we superscript and subscript to distinguish between cohomology, cohomology, and homology, right? So similar to how we look at vectors and covectors, we're looking at cohomology and homology. That's just how mathematics goes. We have duals to everything in mathematics, right? So, okay. The point here that I want to get across is that we are looking at an exact form when we're dealing with the Chern-Simons 3 form, right? So that's this thing right here. Okay. So let's continue here. So this is our Chern-Simons 3 form, right? So I can just write a 3 right here really quick, just to be a little bit more complete. But that's our Chern-Simons 3 form. But if we're just looking at Stokes' theorem in general, what we can, I like the analogy of the fundamental theorem of calculus, where you have their form, right? This dx, we have the d omega 3 here, and that's over this. That's the surface, right? And then the boundary of the surface, right? So, or a volume and the boundary of the volume, right? So this thing here is the volume and the boundary of the volume. And we can sort of think of this again. We could say, in the context of calculus, the points A and B here, right here, A and B, are boundaries on, when we're just looking at a line, for example. If we look at a line or a curve, right, we have A and B, on some Cartesian system. These are points, or the boundaries on some that are 0 dimensions on something that is 1-dimensional, right? So this is 1-dimensional. These things here are 0-dimensional. 0-dimensional. Right, if we're looking at a sphere, right, a sphere is 3-dimensional. but the boundary of the sphere, right, the boundary of the sphere is two-dimensional, right? So inside is three-dimensional, but the boundary itself is two-dimensional. So it's always the volume minus 1, that's going to be the dimension of the boundary. And so same thing here. A and B here define an interval. This is one dimension on a volume, which is going to be 2 dimensions. However many dimensions we're looking at. If our volume is 4 dimensions, A and B are going to define intervals on something that's 3 dimensions, right? So the point here is that this is Stokes' theorem, right? Stokes' theorem says that if we take the exterior derivative, we integrate it over some volume that's equal to integrating something over this function here over the surface. Okay, so cohomology groups help us better understand how exact forms are used in Stokes' theorem, right? So this here is Stokes' theorem. Now we can understand that these things, again, these things are exact forms, right? This is an exact form, right? And it lives in this space right here. So let's continue. So if we use Stokes' theorem then to the instanton number, which is Q, we just get this, right? Because again, this on the volume M4, right? We're in 4 dimensions, 4D. It's the same thing as taking omega 3, which is a Chern-Simons 3 form, on the boundary, right? So on the boundary. Which is 3-dimensional, right? So that's the boundary operator on our 4-dimensional manifold, which is a 3-dimensional thing, right? So the result then is going to be that our theta term, when integrated, is going to be this thing, right? Because we just dropped the d, right? Just drop that d right there, so we don't need that. The point here is that now we have this equation. Our instanton number is equal to the trace of the integral of something on a boundary to for some trace of this thing. And again, these come from a mu equals a, right? So a is equal to a mu a ta, right? That's these guys here, right? That's right, all these guys over here. So, okay, we have a non-abelian gauge field theory now. We're seeing how it's being sort of integrated into this new narrative of topology through this thing called an instanton number. Now, what we're going to do now in the remaining of this video, or in the remainder of this video, is we're going to start taking a look at how this thing transforms, okay? And then we're going to take a look at how and why this thing is quantized, okay? So let's dive into how the Chern-Simons 3 form behaves under a gauge transformation. This will be illuminating because we are going to see that unlike the field strength tensor F, which transforms covariantly, the Chern-Simons 3 form does not. Its transformation law is going to reveal something about the topology of the gauge group itself. So let's start by demanding that we want our covariant derivative to transform in the following way, right? Where this thing is going to be our metric on our manifold. Okay. So let's do this guy here. Again, d mu is going to be our covariant derivative. Right, so d mu, our covariant derivative, is right here with, and we're going to have psi prime equal g psi like this. And this is going to be important later as well. Okay, so let's see here. Here's this, and then we do the same thing over here. Our g being multiplied by our transformation. We can really just follow all of this all the way down. So we have this thing here, right? So this guy here is going to be d mu, right? So d mu, right? So if this thing is right here, this guy is right here, and then this thing is also right here because of the product rule. And then we just do the same thing. A lot of this that I'm showing right now is purely straight up algebra. Okay, so and then we set both sides of these equal because we want this to be true. And we'll see why we want this to be true. We'll see why this is clear later. But we get this, and then really just following the logic here downwards is we're going to have this guy here and this guy here are going to cancel. So we get this, and then this is an arbitrary function, right? So we can just ignore that for right now. And then because that's an arbitrary function, we get this operation here, and then we get this when we we multiply everything by the inverse of g, right? So we're multiplying everything by the inverse of g, and then we get this. And then we just note here that the g times its inverse is equal to the identity, and so taking the derivative of both sides, we get this right here, and then we get this, and then we get this, right? So from all of this then, we're able to plug this result into here, right? So this bit right here, right, that is right here, right? So, and because this is a minus sign, we get a plus sign right here, so we get this. And so from there then, from here we get this, because we're just multiplying by dx mu, dx mu, dx mu. And then we get this thing here, and then we get this, right? Because this thing here, that's just sum over mu, Einstein's sum over mu, right? And a sum over mu again, right? That's the exterior derivative, right? This here is the exterior derivative. Exterior derivative of G inverse, right? And so what we get is this transformation rule right here. So this is the transformation rule for our for our potential, right? So again, recall A is equal to A mu A TA. The transformed A now is this, where this again is this, and now we have the inverse of the metric being involved as well. Right? Okay. Again, you can pause the video if you want, but hopefully that was clear. The two things that we want to keep in mind that we sort of stipulated is this thing right here and this guy right here. All right. Okay, so now we have the field strength tensor, its transformation rule for the potential. The next thing to do is going to be to calculate the transformation rule for the field strength. So let's go ahead and do that. And to do that, again, I apologize for my pronunciation if I'm getting this wrong, but we need to be able to, another tool that we're going to need to do this is to invoke something called the Mourier-Cartan form, or the Mourier-Cartan structural equation. That structural equation is going to be this thing right here, but let's derive this, right? So we're defining this new matrix valued 1 form, right? Because this is a 1 form, right? Because this is 0 form, this is a 1 form. Because when we take this is just a metric, it's like a function on space-time. This thing here is not, right? It's the exterior derivative, which takes us to q plus 1 form, right? So this thing here, we're defining this thing, this y, to be this, right? And there's a good reason to do this, right? Because we see this pop up right here, and it would be nice if we had something, a transformation rule that looked like this, right? That in that case we would have a very nicely behaved transformation for our potential. So let's define this thing and see what happens when we define this thing. right? I don't need to erase that. So for the following proof, we need only three things here, three ingredients. One is the product rule, right? So the product rule, again, is just here, D acting on A and B is the same thing as D acting on A, wedge with B, and A acting on DB, right? And this this can be thought of as a wedge product as well. This is a nilpotency condition, right, where the exterior derivative applied twice is 0. That's something we've talked about as well. And then we have the identity right here, right? So and this leads us to the notion that if we take the exterior derivative of both sides of this equation, we get that the exterior derivative of this is equal to 0. Okay, so let's do the proof, right? So the proof is we start off with dy, so we want to take the exterior derivative of y, and so we do that, right? So here's our exterior derivative operator acting on this thing right here. And then we need to do the product rule, right? So the product rule is going to be this acting on G, right? Acting on G, and then we have our DG inverse, and then this acting on DG inverse, right? And then we know that exterior derivative applied twice is going to be 0. So this is applying nilpotency. Condition. All right. And then when we apply the nilpotency condition, we get this thing right here. Right, because this bit right here effectively goes away. And so we just get this, which is right here. All right, so now we're applying the identity, right? The identity here is the derivative of, or the exterior derivative of this is equal to the exterior derivative of the identity, which is 0. And then we're doing exactly the same thing that we've done right here, right? So that's why I put this in green. But that leads us to this, right? Because this thing here, right? So this guy right here, dg, that is this guy right here. It's when we take dg, right? That's this right here, right? That's that. And so that's going to be this right here. And then we just have this guy right here, which is right here. G is a 0 form or a matrix, so it can pass through the wedge product symbol to multiply the form on its right. Right, so this guy here is we can put it right here because it's, again, it's just a 0 form, or it's a function on space-time. It's a metric, that's what it is. We've covered that before in GR. But from that, then, we get this, right? Because we can just move that G over. And so when we do that over here, we've effectively moved this G over to right here. And then we get this dy equals y wedge y, right? Because this here we defined as y, right? All the way up here, we defined this thing right here. This is y. And so we get this right here. So we're really close. We just take this side to this side to the equation, and we get our Fourier-Cartan equation, and we're going to call that equation 1. Okay, so we have the field strength, we have the transformation rule for the potential. Let's start now by rewriting the transformed potential with all these tools now that we have at our disposal. So one thing that we can do is we can see, here's our transformation rule that we've derived. That's right here, right? This guy right here. So we have this transformation rule. Let's define now this y, which we've already done, okay? And where this is x, okay? So we can rewrite then a prime in this way. And now we can rewrite the transformed field strength. What does this look like? The transformed field strength is then going to be, because it's going to be this, right? Because if we look back over, if we look back over here, where's our field strength? This guy, right? We just do that. We apply this is dA, right? dA, and then A wedge A, right? Here's that wedge, and here's this A, and here's that A, right? So we're just applying all of this to our newly transformed F, or field strength tensor. And so, wedging all this out, we get all this, right? Because this X wedge with X wedge with Y wedge with X, and Y wedge with Y. That's all this. We're going to regroup now. Okay, this is the magic step here. We regroup. We take this guy here, and this guy here, and that's right here. The rest is going to be put into this parentheses. And then we take this then. Here we have these guys, we have this guy, and these guys. Now let's take each and every one of these guys individually and see what happens. This is the hard one here, right? So the exterior derivative of x is this, right? Exterior derivative of this, because this is how we defined x. If we take m to be GA and n to be the inverse of G, and using this right here, because again, G inverse, that's just a zero, that's a zero form. So we're just taking the degree of m, which is going to be 1, right? So this is a general product, or this is a general exterior derivative. I'll just exterior derivative for a Q form product with a P form, right? So if this is our Q form, and this is our P form, it's just the exterior derivative of two of them, the product of two of them. And this is the rule that we have established in previous videos in my GR playlist. And the degree of m, again, that's just 1, right? Because it's just a 1 form. We have a 0 form, and A is a 1 form. So this thing here, right? So this is going to be product rule, right? And this is going to come from here, right? So we have DG, right, with AG, right? So this gets applied to here. We get this guy right here. And then this thing gets applied to my apologies, to this whole thing then, right? Because we get D, this is our M, right? This is M, and this is N, and then here's our M, and here's our N, right? Okay, so we let's bank this equation, because we're going to piece things together, and I know this video is going long, but bear with me here. So now we have to deal with each and every one of these terms, right? So that's going to be this guy here, right? So x wedge x, right? So we defined x again to be over here, this guy, right? So that's here's x, right? And then here's the other x. And then same thing here, so here's x, and here is y, and here is here's y, right? Right, so we defined y, and then here's x. Right, this is just that rewritten form of y. That was right here, right? All right. Okay, so we can calculate all this, right? So G inverse with G, that's just going to be 1, or identity, and so we get this. Same thing here, G inverse with G. That's going to give us this thing right here, and then G inverse with G again, right? And so we can see how this all sort of works out. The yellow and blue no, yellow and blue box don't cancel each other out. That was a mistype on my part. Well, we end up, the remaining transformed field strength is this thing here. We can see that the reds cancel out, the greens cancel out. We can ignore these guys as well. We're just looking at the coefficients here, but we can see that they cancel out, right? And so the result is this right here. We're getting so close to what a transformed field strength, topological field strength looks like. Right, so, okay, so what can we do with this? Well, we have G and G inverse, we have G and G inverse, right? So we can, both of these things are sandwiched. So we just put these two things in and then sandwich them like this, right? And then we can get, now we see that this here, this is indeed F, right? So here, this is it, right? This is our newly transformed field strength tensor. And this was made possible, made possible by d mu on some arbitrary function. Let's just go back over here actually. This was all made possible by making this stipulation right here, that the covariant derivative multiplied by some arbitrary function is equal to the metric times the covariant derivative. So this is like a transformation of d mu. This is like a transformation for our covariant derivative. This is what our covariant derivative has to look like in order for something like this to happen. Okay, and then for our and then we also had this equation here, right? But that was just a stepping stone, right? So that was just a stepping stone to understanding how we get this right here, right? Let's erase some stuff. We're almost done. This proves that the field strength transforms covariantly, right? This is a covariant transformation of the field strength, and it doesn't get messed up by the inhomogeneous term here that we've introduced with y. Apologies for that. My battery on my iPad was dying. But this proves that the field strength transforms covariantly, and it doesn't get messed up by the inhomogeneous term that A does. It just gets rotated by G, right? So, which is exactly what a physically meaningful quantity should do, right? So, the long and tedious path to come is going to be to understand this, how the three form itself is transformed, right? So the three form itself is transformed in a way that looks like this. This is the punchline that we're going to get to. This term is just the untransformed Chern-Simons three form. I'll erase this really quick. This guy right here, this is called the Weiss-Zumino-Witten term. This is the important sort of interesting contribution to the transformation for the Chern-Simons three form that we're going to see how this comes about. And then we have this exact form as well. But that is that. Just so before I hang up here, what we've done is we've now defined this F, right? That was dA plus A wedge A, okay, and the transformation for this is GF G inverse, okay. So that is what we've done. All right, and in doing that, we've said that the covariant derivative acting on some function must transform in like this, right? X mu d mu like this, right? So yeah, and that also our function also transforms gx like this, right? So we needed to make these stipulations in order for this to work, but now that we have made this work, we can proceed on going forward with understanding this, right? So with that being said, I will see you guys in the next video.